Hello students, welcome to Lucky Learning. Here in this video, I am going to explain you multiple granularity locking protocols. In the locking protocols, like two-phase locking protocols, we have seen that locks are going to be done at lower level of data, simply to say data. But the collection of data is forming one record and the collection of records forming one file and collection of files forming a database. This is hierarchy of data. Suppose if we can able to lock data at the higher level, the number of locks to request is going to be reduced. Let us say a record is having 10 data items. Instead of having locks at all the 10 data items, if we have a lock only on record, then one lock is sufficient instead of having 10 locks. That is the advantage of multiple granularity locking protocols. To do this, it requires to allow data items to be of different sizes. And it requires to define a hierarchy of data granularities where the small granularities means smaller sizes of data are nested within the larger ones. And this hierarchy is represented in the form of a tree, and this is also called database tree, where it is representing the hierarchy of data items. And when a transaction locks a node in the tree explicitly, suppose this record is locked by some transaction in exclusive mode, it means all the data under this record, means whatever may be the number of data items, it may have 10 data items, and all the 10 data items also be locked in the same exclusive mode implicitly. Means explicit locks we can request in the higher level, implicit locks by defaultly there in the lower level of the tree. And here granularity of locking is classified into two types, we call fine granularity and coarse granularity. Actually, granularity of locking says level in the tree where locking is done. At what level you are performing a locking. That is level in the tree where locking is done. We call fine granularity and coarse granularity. If locking is done at the lower level, we can call it as a fine granularity. If a locking is done at the higher level, it is called coarse granularity. In a fine granularity, locking at the lower level, so the number of locks are more, we can call locking overhead is there, and high concurrency is possible because multiple transactions can run simultaneously. But when in the case of having locks at the higher level, locking overhead is less, but concurrency is also less. And to implement this multiple granularity locking protocol, we have to understand the hierarchy of data granularities. That hierarchy is represented in the form of a tree. Let us an example database consisting of areas, area 1, area 2. We can also call page 1, page 2, or memory block 1, block 2. And each page can store multiple files, file A, file B, file C, like this. And each file will have records, record A1, A2, dash dash AN. Similarly, each file having records, and each record will have a data. And we have seen locking protocols where locks are done at the data. Now we will see how locks are done at the higher level of data. That's why here the hierarchy is represented in this order: database followed by area, also called pages, and files and records. Then we have a data. Now, how locking protocol is to be implemented? So far, we have only two lock instructions called shared lock and exclusive locks. Using this shared and exclusive lock, how multiple granularity locking protocol is implemented? Is it required to have any other lock modes? And why it is required? What is the reason? Let us say, first, some transaction T1 locks file A in exclusive mode. What is the meaning? File A locked in exclusive mode means all the children of file A also locked in exclusive mode implicitly. So means if n records are there, n exclusive locks implicitly there, right? Explicit lock is done on file A, but implicitly every record is locked in every record is locked in exclusive mode. After that, suppose T2 want to lock RA1 in shared mode. But RA1 already locked by T1 in exclusive mode implicitly, but no information is there with RA1. Because no information is there with RA1, T2 takes a lock on RA1, but which is already locked by T1 in exclusive mode. Now T2 locking in shared mode, causing a conflict. So that the lock for T2 on RA1 should not be allowed in shared mode. It should be wait. Means T2 should wait. Why? Because implicit locking is there on RA1 in exclusive mode. The point is how T2 knows this RA1 already locked by some transaction T1 implicitly in exclusive mode. So before T2 takes a lock on RA1, it has to check what is a lock on its parent. Because the parent is locked in exclusive mode, child cannot be locked in shared mode. This is one reason. Means it has parents of every node before it locks. Suppose a case, suppose a case where uh, this T2, assuming this T2 first taken a lock, later T1 requesting exclusive lock on it. But how T1 knows one of the children of FA is already locked in shared mode? So T1 has to check all the children's, but checking all the children's will take more time. Because it takes more time, this is not feasible solution. Because one of the children of FA already locked in shared mode, this node parent means RA1's parent FA cannot be locked in exclusive mode. What T1 can do? Wait. So it means implementing this multiple granularity locking protocol just by using shared and exclusive locks are not sufficient. Then what we have to do in addition to that, it requires to have intention lock modes. So what intention lock mode should do? The transaction before locking any node, it has to lock its parent node in intention mode, stating that what is its intention. First, T2 should lock database in IS mode, indicating that T2 is going to lock one of the children of database in shared mode. Then come down, T2 should lock A1 in IS mode, and T2 should lock FA1 in IS mode. Then come down, T2 should lock RA1 in S mode. Now next, after that, if T1 wants to have exclusive lock on FA, how it can lock? First, it should lock database in IX mode, indicating that one of the children of DB is going to be locked in exclusive mode. Then lock A1 in IX mode. Then come down and FA, it has to lock in FA in exclusive mode. But on FA already we have one lock by T2 in IS mode. It is indicating that one of the children of FA is locked in shared mode. So no parent of FA means no parent of this RA1 means FA can be locked in exclusive mode. So that what it will do, it will simply wait for T2 to release the lock. So it doesn't require to verify all the children's locks. Correct or not? So that is a benefit of intention lock modes. So intention lock modes are for indicating what is the intention of a transaction to lock a particular node. So in addition to shared and exclusive lock modes, to implement this multiple granularity locking protocol, we also have additional lock modes called intention lock modes. And there are three intention lock modes called intention shared. It is indicating that explicit locking at lower level of the tree, but only with a shared mode. Means some node A locked by some transaction in IS mode means any of the children can be locked by the same transaction in S mode. And what is IX mode? Same thing, indicates explicit locking at lower level with exclusive or shared mode. Suppose a node is locked by transaction in IX mode, one of the children can be locked in S mode or exclusive mode, right? Because IX is for indicating that exclusive lock. Exclusive lock is for both reading purpose and writing purpose. So that if a node is locked in IX mode, its children can be locked in S mode or exclusive mode. And the third one is called shared and intention exclusive. Let us an example. This is a node. It's having several childrens B, C, D dash 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 Z is there. C to Z, the transaction should read it. Means transaction wants to read all the nodes from C to Z. So the transaction should lock C to Z in shared mode and but update B so that transaction should lock B in exclusive mode. And to have shared locks in all these nodes, so instead of having shared locks in C to Z many number of nodes, best thing is transaction can lock that node itself in shared mode, because the same transaction wants to lock B in exclusive mode. Before it locks in exclusive mode, it should lock its parent in IX mode. So what locks are required on same node A? Both S as well as IX. So together we can call SIX mode. Means the current node can be locked in shared mode and one of the children can be locked in exclusive mode. Means remaining children all are in shared mode. For this, SIX mode is suitable. Now we have two locks, shared and exclusive. Along with now we have introduces three locks, that is intention shared, intention exclusive, and shared and intention exclusive. Now, what is the compatibility of these lock modes? It is a compatibility matrix of all the lock modes. Let us see one of the row I will explain you. Suppose some transaction T lock this node in shared mode. Let us say T1 locked this node in shared mode. What is the meaning? All the children of A also be locked in shared mode implicitly. And so any other transaction T2 wants to lock B also in shared mode. Is it possible or not? Yes. If B is locked in shared mode, its parent is to be locked in IS mode so that S and IS is compatible. These two are compatible. But suppose if T3 wants to lock one of the children of A in exclusive mode, A is already locked in shared mode. Any children of A can be locked by T3 in IX mode? No, not possible. Why? Because all children of A already locked in S mode means the no children of A can be locked in mode. That's why it is false. And T4 wants to lock A in shared mode. And we know that shared and shared is compatible directly. And T5 wants to lock A in SIX mode. What does it mean? T5 can lock A in S mode. T1 already had a lock on A in S mode. S is compatible. But no children of A can be locked in exclusive mode. IX says one of the children of A also can be locked in exclusive mode. That is not possible, so that it is false. And we know that directly, if any transaction is wants to lock A in exclusive mode, not possible because shared already there, exclusive is not compatible. So what are the compatibilities with shared lock? Shared is compatible with IS and S. Remaining all are not compatible. Similarly, you can check out all the compatibilities between the locks. And when it comes to the exclusive locks, it is not compatible with any one of it. When it comes to IS lock, it is compatible with all except exclusive locks. And IX is compatible with IS and IX, not compatible with remaining modes. And SIX is compatible with IS, not compatible with anyone. X is not compatible with anyone. You can remember in this way for the exam. IS is not compatible only with X. IX is compatible with IS and IX. S is compatible with IS and S. SIX is compatible with only IS. X is not compatible with anyone. Remaining all are not compatible. False, false, false. Now, how locking can be done in multiple granularity locking protocol? That to perform a lock by a transaction Ti on some node Q, it has to follow some rules. First rule is lock compatibility matrix must be observed. Compatibility should always be satisfied. And second, the root of the tree must be locked first. Why? Because locking always done starting from root to leaves. Root to leaves. And a node Q can be locked by Ti in S or IS mode. Suppose this node A to be locked by Ti in S mode or IS mode. When this is possible, the parent of this node, assuming B, is to be locked by same transaction Ti in either IX mode or IS mode. So IS S possible, IS possible, IX S possible, IX and IS is also possible. And a node Q can be locked by Ti. Look at this is a node Ti locked A in X mode, SIX mode or IX mode. When only if the parent of Q is currently locked by Ti. Suppose the parent of A is B, it is locked by Ti in IX mode and SIX mode. Means if parent is IX, child can be X or SIX or IX. If parent is SIX, child can be X or SIX or IX. Possible. And Ti can lock a node only if it has not previously unlocked any node. It is meaning that suppose Ti locked A, then B, then C, and then unlocked B, it never continues with lockings. So means first it has to take all the locks, then it has to perform all the unlocks. That's why this multiple granularity locking is also called two-phase locking protocol. And last point, Pi can unlock a node Q only if none of the children of Q are currently locked. So means when unlocking of B should be possible after unlocking of C. When unlocking of A should be possible after unlocking of B. So means locking is from root to leaves, unlocking is from leaves to root. Unlocking is from leaves to root, right? And observe that locks are acquired in root to leaf order, whereas the released in leaf to root order. This is how locking is going to be done in multiple granularity locking protocol. And hope you understood this lecture very clearly. If you understand, if you like the video, please share with your friends. And one more important thing, this notes is totally available in the form of PDF and the link is available in the description. Please download it after listening it so that you can easily write the answer for multiple granularity in your exam very easily. Thanks for watching. Thank you.